So related rate problems are problems that we look at how one variable is changing with respect to time in comparison to how other things are changing with respect to time. And they get a little bit complicated. Sometimes the biggest problem that people often have when they're doing related rate problems is they try to plug in numbers of things that are changing before they do all their calculus work. So when we have a related rate problem, what we're first going to do is just try and figure out what we're looking at, what we're talking about, what's going on in the situation, and then draw a picture and label the things that are important to the problem. But when we label our picture, the only things that we want to label are quantities that are constant. Okay? So if I know that the distance between where I'm standing and where a bullet is being fired out of a gun, I know that distance is 100 feet. That distance isn't changing, so I can label that, right? But if I'm talking about the angle that bullet takes as it moves away from me or something, that angle might be changing, and so that we'll want to not label. We'll just label it with a variable. Does that make sense? So if something's constant, we'll label it. If something's not constant, we won't label it. Then we just need to write an equation that relates the variable that we want to know how it's changing to all the other variables, and then we'll differentiate with respect to time. So the differentiation that we do with respect to time is sort of freezing the problem at a single instant that we're interested in. So we're differentiating with respect to time at an instant to look at what's going on in the situation at that exact moment. Then we'll do some substitution of some numbers in and solve. So I don't know if it sounds complicated. It might not sound complicated, but we're going to start with one that's fairly easy, and I think it should sort of help you get going with this. So we're going to have a hot air balloon. It's going to rise straight up from a level field, and we're going to track it at a distance of 500 feet from where it's lifting off from. And then we got some other stuff going on. We want to know how fast the balloon is rising at some specific moment in time. So let's draw a picture. Here is me. I'm a dot. Here is where the hot air balloon is rising straight up into the air. Look at that. Look at that balloon. Isn't it nice? We are interested in how fast the balloon is rising. So that's the change in this distance, right? And what do we know that is not changing in this problem at all?
The distance from you to the balloon, or where it started.
Right, the distance from me to where the balloon started. We know that's 500 feet. That is not changing. So I'm going to label that as 500. That's a constant quantity. It will stay like that. We're also given some information about the angle of elevation from where I'm standing watching it to the balloon. Oh, that didn't really hit the balloon, did it? There we go. So is this angle here changing?
Yes.
Yeah, that
Yes.
angle's changing. So we are interested in how fast the balloon is rising when that angle is pi over 4, but that angle is not always pi over 4, right? So that angle, we'll just label it with a variable. We'll label that angle with theta. And we'll deal with that later. Okay. We're also interested maybe in what this height is, because we're talking about how fast this height is changing. So we'll worry about that in a second also, but that y value is also changing. So then we're going to label whatever known quantities that we have. So we know that we're interested in theta being pi over 4 radians, right? So I'm going to write that off to the side. That's what we're interested in, is theta being pi over 4. And we want to know how fast y is changing. So we want to know what's the change in y with respect to time, or what's dy dt equal. And there's one other piece of information that we are also given. What is that?
How fast the angle is increasing.
How fast the angle is increasing. And that ought to be a change in the angle with respect to time, and that's 0.14 radians per minute. Now, I want to make a note right now. I'm going to tell you guys this. If you have an angle and that angle is changing, and it tells you that it's changing at some number of degrees per minute, you need to change that into radians before you can do anything with it. Okay? You must change it into radians before you do anything with it. Radians are a real world measurement, whereas degrees are not. So we have to have it in radians. Okay. So everybody feel relatively comfortable about what we've drawn and what we're doing here?
Yeah.
All right. Now, how can I relate the three things that I have in my picture to each other? Is there an equation that I could use to relate them?
You could use some trig with the angle and the opposite angle, or the opposite side and the 500.
Okay, so what trig?
Be tangent.
Yeah, tangent theta ought to equal y over 500, or effectively y ought to equal 500 times the tangent of theta. Everybody agree with that?
Yeah.
Okay, so now we've got an equation that relates all of the stuff that we're given in the picture that we know, and we're just going to differentiate it to freeze it in time at a specific moment. So when we take the derivative with respect to time, it freezes it at whatever time we want. So the derivative of y with respect to t is dy dt, right? That's an implicit differentiation thing, taking a derivative with respect to t. What about the 500 tangent theta? That ought to be
Y.
500
Secant squared theta.
secant squared theta, but I took the derivative of something with a theta with respect to time. So it should be 500 secant squared theta times the derivative of theta with respect to time. Does that make sense to everybody?
And then we're going to solve for d theta dt later, and then we plug that in. Is that?
No, we're going to solve for dy dt. We have d theta dt already.
Oh, we have it. Okay.
So we knew what theta was when we were interested in the speed of the balloon rising. And we knew what d theta dt was at that moment. So we just plug those in to find dy dt. So dy dt ought to equal 5 times secant squared of pi over 4, because that's the moment that we're interested in, times 0.14. And what is the secant of pi over 4?
Square root 2.
Square root of 2. And if we square that, it ought to just be 2. So we got 500 times 2 times 0.14, 1,000 times 0.14, or what does that come out to be?
$140.
140 feet per minute, I believe. Our angle was increasing in radians per minute, and our distance was in feet. So 140 feet per minute. Good or no?
Good.
All right, that's related rates in a nutshell. They get a lot more difficult than that, but that's the basic idea of what a related rate problem is. Read it, figure it out, draw a picture, label the things that are constant, label everything else with a variable, write an equation to represent the situation, differentiate with respect to time, and plug it all in. Everybody good there?
Yep.
All right, let's do another one. So I'll give you guys a second to read through it. And in fact, I'll give you guys a minute or two here to read through it and see if you can draw a picture to represent what's going on. And then in about 2 minutes, I'll help you guys draw the picture and we'll label what all would need to be labeled. You guys got a picture of this or no?
Yeah.
Hopefully, yeah. All right, so we got a police car approaching a right-angled intersection from the north. So here's my police car coming down this way. It's chasing a speeding car. That car has turned the corner and is going east, so it's going this direction. It's a right-angled intersection. That angle is not going to change, so I'll label that right now. And we know that when the police car is 0.6 miles north, the speeding car is 0.8 miles to the east. So is that 0.6 miles north, is that a distance that's changing?
Well, if the police car keeps moving, yeah, but
Right, the police car is moving, so that distance is changing, right? That distance is decreasing. And what about the speeding car that's 0.8 miles to the east? Well, yeah, it's continuing to move, right? It hasn't hit a spike strip and come to a halt, right? It's still moving also. So that's changing. So we'll leave that alone. We won't label that yet. We know that the distance between the two cars is increasing. So that's this distance. We know that distance is increasing at 20 miles an hour. So clearly it's increasing, so that must be changing. So we won't label that yet either. We also know the police car is moving at 60 miles an hour at the instant that we do this measurement, and we want to know the speed of the car. So let's label some variables on here. How about we'll call this one X, since this distance is changing, and this one Y, since that distance is changing. And how about Z, since that distance is also changing? Sound good? Hopefully that's the picture you drew. Yeah. There's not much else to put on it. Although we can, off to the side, say that Y is equal to 0.6, right? At the moment we're interested in. X is equal to 0.8 at the moment we're interested in. And that the distance between them, which is dz dt, is increasing. So how is it changing? It's increasing at 20 miles an hour. We also know that the police car is moving. So that'd be a change in y, dy dt, should be equal to what?
20.
60.
60. But there's a problem with making that 60. What's the problem with making that 60? what does dy dt represent? It represents the change in y with respect to time. What's happening to y? Is it getting bigger or smaller?
Smaller.
Smaller, right? If I said that dy dt, the change in y with respect to time is 60, that would indicate that it was getting bigger. But since that distance is decreasing, we're going to say that that is negative 60. Everybody good with that? So anytime the distance is decreasing, its rate of change has to be negative. And if the distance is increasing, like dz dt says it's increasing at 20 miles an hour, then that's a positive value. Everybody good with that?
Yeah.
Okay. So how can I relate these variables that I have in this right triangle?
Pythagorean theorem.
Pythagorean theorem. X squared plus y squared equals z squared. Okay. And now we've got a formula that relates them. All we have to do is take the derivative of it with respect to time. So what's the derivative of x squared with respect to t?
2x.
2x dx dt.
And the 2y ought to be, or sorry, the y squared ought to be 2y dy dt. And the z squared ought to be 2z dz dt. Everybody good with that?
Yeah.
Cool. So now we'll plug in everything that we know. 2 times our x value, which is 0.8, times the dx dt. Well, what's dx dt? Dx dt is how fast the car is moving. That's what we're interested in. So perhaps over here I should have written dx dt is what we're looking for. So 2 times 0.8 times dx dt plus 2 times y, which is 0.6, times dy dt, which is negative 60, equals 2 times z. Now we don't have z, times dz dt. So if we don't have z, what do we need to do to find z?
Plug in x and
You
y,
use-
solve for z.
Yep.
Yeah.
0.6 squared plus 0.8 squared equals z squared. What does z come out to be?
1.
1. 1. So z is 1. And so now we end up with 1.6 dx dt equals, what is this, 40, and then plus, what is that? That's 1.2 times negative 60. That ought to be 72. And what do we end up with for dx dt? We got 112 divided by 1.6. What's 112 divided by 1.6?
$70.
70. So 70 miles an hour. Good or no?
Good.
All right. Any issues with that?
So any like values that are changing are derivatives.
Any values that are changing with respect to time, yeah, are only plugged in once we take the derivative. Yep.
Okay.
Why is the distance between the two cars? Or never mind, actually.
Okay.
Yeah, I got it.
All right. All right, let's do another one. So I'll give you guys a minute or two here to read it and see if you can draw a picture of this one as well. How do we feel? We got a picture? We good?
Yeah.
All right. So first off, we got water flowing into a tank that is a cone. So here's our cone. It says the tank is standing with the point down. I didn't do that very well, did I? There we go. That's perfect. That cone has a height of 10 feet. So that height is not actually changing, right? And it has a base radius of 5, which is also not changing. But we want to know how fast is the water level rising when the water is 6 feet deep. So that 6 feet deep, that is certainly changing, right? So we could call this distance here the height or the depth. How about height? And then we've got some other radius here. Everybody good with that picture?
Yeah.
Okay. So what information are we given? We're given information that the water level is rising and that we're interested in the height being 6. And we're looking for how fast that water level is rising, which would be a dH dt, a change in height. What else are we given? We're given that water is flowing into the tank at 9 cubic feet per minute. What is that?
Volume.
That's a volume, right? And you can be clued in first off by the units, right? Cubic feet per minute. But that's dV dt is 9. So we need to somehow relate volume to height. So first off, what's the volume equation for a cone?
1/3 r squared a.
1/3 pi r squared h. Okay, well, what's the problem that we've got here? Are we given anything about a radius?
No.
Other than that the base radius of the cone is 5. Nothing about the volume of this as the water level is rising. So somehow we've got to turn that r squared into terms of h. So how are we going to do that?
Maybe use like the initial height and radius to write like a proportion.
Yeah, it's exactly what we're going to do. We're going to use those to write a proportion. The reason we can do that is that these are similar triangles, right? This is going to have a right angle here, and this is going to have a right angle here, right? Because the top of the cone should be flat, and the water level should also be flat. And so they share this angle in common. So they have two angles, this angle and the right angle, that are congruent to each other, which makes them similar triangles, which means that the ratio of the radius to the height of the big cone ought to be equal to the ratio of the radius to the height of the small cone that we get as it fills up with water. And so what does R equal?
3.
3.
Well, okay, so R equals 3, but I'm saying in terms of H, what does R equal? Should be
Half of
H
H.
over 2, right? Because we don't
Yeah.
want a specific number for this radius to plug into here, because that radius value is changing. So if I plug a number into here for something that's changing before I've taken a derivative, that's a problem. We can't do that. So what we need to do is we need to replace the R with H over 2, and then we'll be able to do that. Everybody good with that? So 1/12 pi h cubed. Good or no?
Good.
Okay. So now we'll take our derivative. dV dt ought to be equal to 3/12 or 1/4 pi h squared dH dt. And what value are we looking for? We're looking for dH dt. We'll just plug everything else in. 9 is 1/4 of pi times the height, 6 squared. And what do we end up with as dH/dt? Multiply by the 4 is 36, right?
1 over
Divide by the
pi.
36 is 1. We just get 1 over pi. And this is feet per minute. Good or no?
Did you get the 9 from the original problem? Is that where that came from?
Yep,
Or-
dv dt equals 9. So we just replace the dv dt with 9. And that's related rates. That's how you do related rate problems. Any questions on that?